Welcome back. So previously we talked about the layers of the Earth. We talked about the driving mechanism of mantle convection, moving large plates that make up the crust on the surface of the Earth around. So how do we know this? Well, how did we start to investigate this in the first place? How did we come to the understanding that, wait a minute, these things are moving? Well, let's talk about some of that proof that we originally looked at before we understood, that Earth's surface changes. So this is an image of what a past, what's known as a supercontinent looked like. This is Pangaea or Pangaea, meaning all Earth. It's Latin for all Earth. This is a time when the continents were all smushed together. This actually happened a number of times throughout the past. Pangaea or Pangaea was not the only supercontinent. There's many that came before this. This was just the last one that occurred. Therefore, it's the one that most people know about if they have kind of heard of any supercontinent. They've heard of Pangaea or Pangaea. But how did we know the Earth looked like this? What proof do we have that we can fit these pieces together? If we were to superimpose today's countries on Pangaea or Pangaea, this is kind of what it would look like. Here's the United States. It'd be just a short trip to Africa or South America. Everything would be right there. So how do we know this is what Pangaea looked like? And I'm sure some of you have learned about this in the past, but or thought about this. It looks like the continents kind of fit together like a big puzzle piece. They kind of fit together nice and neat. Well, how do we know? Well, what makes them fit so good? Well, when we're looking at fitting together the continents, if you look at the shapes of, for instance, South America and Africa, it looks like they kind of fit together. Not perfectly, but they do. So that brings the question, well, where does the end of a continent? Have you ever thought about where does our continent end? I'll give you a hint. It doesn't end at the beach. It doesn't end at the shoreline wherever the ocean hits. In fact, the true edge of the continent extends all the way out to the edge of the continental shelf. This is the true edge of the continental crust. This is the true edge of the continent. So over time, weathering and erosion, as the process of rock material being broken down and transported away, that occurred due to ocean movement, ocean waves, storms coming in, just battering and breaking down the rocks. So over time, over millions of years, billions of years, the edges of the continents kind of get ground down and covered with ocean. So it's a relatively shallow ocean. Now, the continental shelf can extend for a few miles. It can extend over 100 miles, just different places. For instance, the North American plate on the east coast has an extensive shelf, whereas if you look at the African plate, not much of a shelf. So there's some factors that go into that. But if we fit the continents together, they kind of fit. But when we consider the continental shelves, if we include that, they fit together really, really well. So looking at the kind of the lighter beige and the lighter other beige, I don't know why they're both kind of this color. But if you look at together these lighter colors, if we consider those, these continents fit very well together. So the shapes are some good evidence that, guess what? The plates were together in the past. They're not now, therefore plates move around. However, when we consider the continental shelves, that fit becomes even better. So a great piece of evidence that, maybe one time these were together. They're not now, therefore that's proof that plates move. But that alone, that might just be coincidence. What else you got? Well, again, looking at South America and Africa, these two different continents, looking on either side of them, the ages of rocks on either side of these continents tend to match up. So a little bit about 550 million years old. You see this little bit that's older in Africa actually dip down into South America in this little section, which on its own is weird, but when you put these together, they kind of match up. So again, that's some great, possible evidence that these were once together. Now they're not, therefore plates move. And that's okay. That's two pieces of proof. Hey, you got any more? Yeah. Geologic formations. Looking at North America, Africa, Europe, there's some mountain ranges that, for instance, the Appalachian Mountains on our east coast, well, on their own, that's great. But when you put the continents together, this kind of formation, this mountain range formation kind of lines up, kind of showing that, this might have all somehow been connected. And looking at the ages of the rocks, we can find places that are younger or older. So that means, at times, the portions of these mountain ranges were formed at the same time. How did that get to be? Well, did they each happen independently, randomly on these separate continents, or was it when they were all together somehow? So, 3 pieces of information, 3 pieces of proof. Fossils, let's make it 4. There are, typically with living organisms, what type of organisms live in North America are different than the type of organisms that live, for instance, in Australia. For example, kangaroos, koalas, those sorts of things. Those only live in Australia, not here, naturally. The reason being, as the evolutionary process took place, different organisms evolved differently. So, when we look at fossils, typically we find different fossils on different continents. However, there are some fossils that we tend to find on what we now know as very different continents, which doesn't quite make sense. A good example is a type of tree, and these leaves from the Glossopteris tree. We have different trees in North America than they do in Australia. But to find these fossilized leaves in South America, Africa, Antarctica, that's weird on its own. Australia, part of India, it's weird to find these fossils of the same tree in different places. Typically, you would have different trees, different animal life. But, again, when you kind of put them all together, it makes more sense that these trees existed in this range instead of independently somehow evolving on South America, Africa, India, Australia, and Antarctica. On top of that, Antarctica is cold. There's no trees there now. How was there fossils of leaves on Antarctica? Why did we find fossil evidence of leaves there? Well, it tells us Antarctica must not have always been there. Antarctica, the continent beneath all that ice, must have been somewhere else, someplace a little bit warmer for it to have the ability to have trees with leaves on it. Not now, so therefore Antarctica must have been in somewhere else in the past. Again, this is all evidence that in the past plates were somewhere else. They're not now, they're separated now, therefore they must move. Mesosaurus, another fossil. There's a number of fossils you can look at. Lystrosaurus, Sinognathus. So there's a number of different fossils that on their own, it's weird to find them on different continents, but if we recreate and mush these continents together, it makes much more sense because we can kind of see the patterns to these fossils. By the way, Lystrosaurus, just a side note, it's just super cute. Look at that little guy. Oh, it's like a little puppy dog. Look at it's like a little puppy dog. Anyway, you want more evidence? Let's do it. More proof of movement. Glacial striations. So there's glacial evidence. These striations, these scratches. Glaciers can be many miles thick. Ice, when it gets that thick, can cut through rock like a hot knife through butter. As these glaciers move over an area, they could just grind even whole mountain ranges, just straight, smooth, and flat. So as you get glaciers moving in a certain direction, they'll carve the rocks underneath it. Over time, as those glaciers melt away over thousands or millions of years, you're left with the rocks underneath that have these weird scratches in it. And they indicate the direction in which the glacier was kind of moving and flowing. So you get these what are called glacial striations. It's weird to have these striations in Africa. Why? It's hot there. There's no glaciers there now for the most part. India, it's hot there in the southern part of India. There's no glaciers there now. Australia, it's hot there. There's no glaciers there now. This part of South America, it's hot there. There's no glaciers there now. Wait a minute. How were there glacial striations there? Well, then all of these places must have been somewhere else, someplace where it was cold enough for there to be glaciers. They're not now, therefore they must have moved away from that location. The direction of these glaciers or these glacier striations are indicated by arrows. Seemingly random, but again, when you put it all together, these glaciers kind of all flow out from centralized location. In this case, the North Pole on Antarctica. Let me say that again, the North Pole on Antarctica. Every so often, the magnetic north and south pole of the Earth flips. So at this point, Antarctica was the North Pole, because that was the magnetic North Pole. Magnets have poles, north and a south. It's kind of a side note, but it's on there, so just something interesting as it may pertain here in a few more slides. So when you put all of these continents together and you see the direction of the glaciers kind of radiating out from one point, oh, that makes sense. That whole area must have been covered by glaciers. Look at that perfect kind of shape that it forms. That whole landmass must have been somewhere else, somewhere where it was colder. It's not now, therefore plates move. So evidence of Pangea, that's evidence of past supercontinents, which we don't have now, therefore plates must be moving, are the shapes of continents, ages of rocks, geologic formations, fossils, and glacial striations. But what's the proof of plate movement now? Like, how do we know they're moving now? Okay, so there was a supercontinent. There's not one now, so plates did move, but how do we know they're still moving? What's that current piece that shows us, yep, the plates are still moving? Well, number one, we can look at something called seafloor spreading. In the mid-1900s, so 1950s, etc., when submarines started to become a viable tool for the Navy, we would map the seafloor, kind of giving submarines, since they don't have windows, kind of a map of what the seafloor looks like. Is there any mountains, any valleys to watch out for as they're kind of floating around under the water? So as we did that, what the Navy kind of noticed is that running along the middle of some oceans in some areas were these giant kind of splits, and ridges right in the middle of the ocean. Well, what they found were these rift valleys at these mid-ocean ridges, places where the plates are spreading apart. We talked about it in the previous unit, where that mantle convection is creeping up and pulling that hot, sticky Play-Doh mixed with rocks, kind of pulling at those plates as that mantle material is rising and kind of moving out of the way before it descends. It's pulling on those plates, ripping them apart. It's what's known as a divergent boundary, where plates are moving away from one another. So we see this. So it was mapped, and we found these splits showing actively where plates are being pushed apart and where new oceanic crust is being formed. This is a decisive piece of evidence. So we see it happening in real time. So we're looking at, as the rocks closest to this mid-ocean ridge, this spreading center, this rift valley, are young, and as you get further and further away in either direction, the rocks get older and older and older. So brand new rock forming right at this rift. Here are these pluses and minuses. We can also see in the rocks how long, or for over what period of time those magnetic poles, north and south, were flipping back and forth, and that happens, like I mentioned, it happens all the time on Earth. Every few 100,000 years or so, you get a flip in the magnetic poles or so, give or take. So anyway, so that's one piece of current proof that we see this happening. Okay, plates move around. And then let's use some technology. What about GPS? It's a valuable tool. It's not just for your phone or finding your way. We can track plate movement as well. So points on a particular tectonic plate will all move in the same direction. So for instance, looking at North America, the majority of North America sitting on the North American plate, we can track any spot on North American plate and see that it's kind of moving to the southwest. However, there are parts of California which are on the Pacific plate, and that Pacific plate is kind of moving up to the northwest. So we actually see parts of North America are moving in different directions because parts of North America are on different plates. Small slice of California is on the Pacific plate. Most everything else of the United States is on the North American plate. So we had evidence of past movement. They're not connected. So we have evidence in the past that continents were connected. They're not now, so therefore plates must move. Also, we have current proof right now. We can see the seafloor spreading happening. We've mapped it. We can GPS and track these continents moving around, so we can track it. If you would like to watch a beautiful dance of the plates moving around, please watch this video. It shows kind of all the plates moving around in the past, going back hundreds of millions of years. Pangea, as mentioned, was just the last supercontinent. There's been many more before that. So this kind of shows you and illustrates all of that. And it's the same evidence we had, just to kind of recreate those pieces and puzzles. And then I always get the question, well, what's the Earth going to look like in the future? So about 150 million years from now, here you go. So you got Africa kind of cruising north, crashing into Europe, pushing it further north, kind of Asia kind of sliding down. Australia's going to crash into Antarctica. Antarctica's going to move a little bit. North America, South America kind of shifting a little bit as well. So there you go. And how do we know that? We just use the current movement, put it in fast forward. There you go. All right, so we're going to pause here. When we come back, we'll talk about how one plate moves relative to one another, how the plates interact, crashing in, pulling apart from one another. And so we'll take a look at that in just a second. I'll see you in a minute.